Okay, hello everyone. I'm Zhou, and I was from Michigan State University, and now I'm an assistant professor in Missouri SNT. This work is collaborated with my advisor, Dr. Qiben, Dr. Zhiyan, Eshan, Dr. Ning, Zhang, Dr. Huacheng, Zeng, and Alireza. So today I would like to share this paper, which is called Breaking the Charge, Exploding State Manipulation in EV Charging. So let's get started. So what is electric vehicle? Electric vehicle, basically, they are trying to use the battery as the power to drive on the road. And electric vehicle has become one of the promising solutions to the environmental and energy crisis. And from the report, we can see that electrical car sales continue to break the record globally, particularly in China and other emerging economies. And besides of that, we can say electrical vehicles is not only on the private cars, but it also have electric buses and vans and trucks. This is the map in the Seattle area. You can see how many EV charging stations are around. So that means the EV and EV charging becomes really popular nowadays. So there are two types of EV charging. The first type is called AC charging. Basically, it uses low voltage to charge the vehicle. And the other one is called DC charging. Basically, it uses the high DC power to directly charge the vehicle. For example, those kind of Tesla charging points. I have summarized some major charging standards here. You can see there are basically 5 different types of standards in North America, Europe, China, Japan, and Tesla. We can say that for AC standard and DC standard, they are kind of similar, but there are still some difference there. Now I'm going to talk about some limitation in attacking EV charging from the existing work. There is one work using electromagnetic injection attack to attack the sensor and actuator in the AC to DC power converter. And there is another work, they also utilize this technique to force the sensor rating to mislead the feedback system. And there is some also work trying to eavesdrop the attack on DC charging. For example, captures and interpret the digital communication between the EV charger to recover those private messages. However, there is a problem currently. Majority of the paper, they are focusing on the DC charging security, whereas they have left the AC charging behind. Therefore, there is an open problem here. It is that how can we launch attacks on AC charging as well? So this is a focus of my work. Basically, we are focused on the AC standard here in the North America because we are in US. That's why this paper are more focused on the SAE J1772 type 1 standard. You may want to ask the difference between this work and the last work that the presenter presented. The difference is that we are focused more on the low-level communication security instead of high-level. They are more focused on the high-level layer. Okay, so in order to propose our attack, we have proposed this ChargeX. It is a new class of attacks which aims to manipulate the charging states of EV chargers with the goal of disrupting the charging schedules, causing the denial of service or overcharging and undercharging the battery. As you can see, this is basically the layout of the overview of our attack. We basically have this malicious extension cable being connected with the benign cable here, and the attack circuit is hidden in this yellow part. And to be more specific, we have shown how it is embedded in the in this location. You can see this is one of our attack circuit, and we embedded this attack circuit in these parts. This is very small actually, and it can be fully hidden in here. Before I continue the design of my attack, I'll briefly introduce of the basics of SAE J1772. You can see from this figure that it has basically 7 pins. This is a DC combination connector, and this part is the charger. So why I put the CCS combo 1 here, it is because CCS combo 1, it is very similar as AC charging, which is type 1 J1772. Without this 6 and 7 pin, which is the DC level power, it becomes the type 1 J1772 connector. And this pin 3 and pin 4 here is ground pin and also the control pilot pin. To be more specific of how this pin located and connected with the charger part and the EV part, we have this layout. Since our time is very limited, I will just briefly introduce how it works. Basically, we have different stage here, charging stage here, and it is based on the high pilot voltage. If the pilot voltage is 12, then it is in stage A, and if it's 9, then it's stage B. For different stage, it's basically saying that it's connected, or the EV is detected, or EV is charging, so on and so forth. And this voltage is measured from pin 3 and pin 4. And if you see this network, you can see for the charger part, the R1 and R3 and R2, they basically form a voltage divider network. And based on the different like the register connected to the network, the circuit basically, the voltage between 3 and 4, pin 3 and 4 will change, and the EV will be charging or uncharging or stop charging. Okay, so based on this, we have our design, 2 types of design, which is called serial insertion attack and parallel attachment attack. You can say from these 2 design here, we basically put a like attack resistor here, just simply attack resistor here, and then we are trying to manipulate the voltage between pin 3 and pin 4 on the charger side and EV side, so that the charger and EV, they will have different sense a different voltage, and the charging will be foul. We also have a attack automation design, because we do not always want the human in the loop to launch this attack. Therefore, we have this design. This design as well. And basically, this attack circuit is trying to draw more current on this R1, so that it will lead the state switching due to the job of EVSE. We have evaluated our attack in the lab setting using a simulated vehicle and real-world setting using a Tesla Model 3. And we evaluated AC home charger level 1 and level 2, and also the AC public charging station as shown in this figure. And we initially set the benign state in state B or C. Before we launch the attack, we are trying to exploring the upper bound to guarantee the success of the attack using a potentiometer, and we found the switching voltage between state A, B, and B and C and F. And we are trying to use this voltage to estimate the operation range of the attack resistance. And here is the performance of the state switching attack. And you can say in most of the case, measures resistance range fall within or match the estimated range in all attack scenarios. And we also have evaluated our attack on Tesla for the serial insertion attack on Tesla and parallel attack on Tesla. And we found for the serial insertion, we can cause the Tesla to have a low pulse voltage error or communication error. And for the parallel attack, we can have make the state changing. We also make the state switching attack successful. Here is some real visualization examples. Yeah, we actually have also an attack demo here, but I don't think I have enough time. So, yeah. Yeah. Thank you. Yeah, thank you.